So our next speaker is Matthew Morrow. He'll speak on perfectoids and tilting.
Thank you very much. So I'd like to thank the organizers for very kindly inviting me to give a slightly unusual talk at your conference. So my goal in this talk is try to present you some overview of this theory of perfectoid spaces and the tilting correspondence. So this is the theory that Peter Scholze has been developing in recent years. In particular, nothing in this talk is due to myself. And I hope at times to give this overview a slight leaning towards the topics of the conference, though I myself am far from an expert in the model theory of valued fields. My suspicion is that many of you have heard some ideas about perfectoid spaces and tilting, have some idea that it lets you move things between characteristic 0 and characteristic p. So I'm going to try to make precise statements in this talk to give you some better idea to how this machinery works. So let me fix right off the bat some prime number and define, so that we have something to talk about, perfectoid fields. So a hypothesis that we'll see a few times is that of having a field which is complete under a rank 1 valuation. Unfortunately, contrary to standard notation, it seems model theory of valued fields, I'm using multiplicative notation for the absolute value, even though I'm going to call it a valuation. Well, there we are. So given such a field, we say that this is perfectoid if and only if satisfies the following 3 conditions. So firstly, I ask that f has residue characteristic p. Secondly, I impose this type of deeply ramified hypothesis that every element of the ring of integers mod p admits a p-th root. And thirdly, as we'll see in a moment, to avoid small examples, I insist that the value group gamma is not discrete. So a few remarks and consequences concerning these conditions and some examples. As was already remarked in a talk on Tuesday, these are of course not first order conditions. In particular, the lack of this being first order condition all comes from this underlying hypothesis star, because I can neither ask that my field be complete nor that it be rank 1 in first order language. So we could weaken these. I mean, I could drop this rank 1 hypothesis and I could replace completeness by Henselianness, and then you start going in the direction of what are called deeply ramified fields. But I'm not going to do that. I'm going to stick to the, I don't want to say classical, but standard case of perfectoid fields. Secondly, what happens in characteristic P? So if I take some complete rank 1 valued field of characteristic P, then it's perfectoid in this sense if and only if it is perfect in the usual sense. I guess I should say perfect and non-discretely valued. Otherwise something's going to go wrong. Let's say not even non-trivially valued. It could be trivially valued. So I can be even more strict and say non-trivially valued. As soon as I'm non-trivially valued, then I've got to be non-discretely valued. Certainly I'm residue characteristic P, and if I'm perfect, then everything has a P root. Forget about the mod P. So the goal of these perfectoid hypotheses is to somehow extend the notion of perfect field to the case of characteristic 0, like mixed characteristic fields. So concerning some examples, we could take QP, I can adjoin to it all P power roots of P, and then because I've insisted that the field be complete, I'd better pass to the completion. I could do something similar where I instead adjoin all P power roots of unity. Joining all P power roots of unity, it's not quite that's not true. It's somehow the maximal P abelian extension. So let me just stick to it like that. Or I could go even further. I could pass to the...
What does that mean, that last one?
These are zetas. So I join all P power roots of unity.
Zeta.
Sorry, it's all for curly zeta. Yeah, it's true. Okay.
It's a curly zeta.
It's a curly zeta. But all zetas are a little bit curly, aren't they? Okay, or I can go all the way up to the algebraic closure of QP. And again, I've got to p-adically complete it. And that's what we would call our p-adic complex numbers. Or an example in characteristic P, I can take my sort of completed field of Laurent series in which I allow, well, for me, this is already complete. Okay. We can argue about, okay, if you do perfectoid things, that's already complete, but it's just notation. I mean, I take QPT, I take FPT, excuse me, I adjoin all P power roots of T, and then I complete the result. Here are some non-examples which have been carefully discarded by imposing suitable hypotheses. Neither FP or QP are perfectoid. In both cases, because they fail this discreteness property on the value group. But if we dropped that, then they would in fact satisfy 1 and 2. So that's one of the reasons we impose this type of hypothesis. So this second condition, that everything has a p root mod p, is combined with the third condition, ensures us that we have lots of p ramification occurring in the field. So in particular, if f is perfectoid, then the value group is p divisible. One might as well give a quick proof. So the fact that gamma is not discrete tells us that it is generated by all the elements which are sandwiched strictly between, well, let's say strictly bigger than the absolute value of p, and which are integral. And for such a gamma, so I write it as absolute value of some x, I can pick a y such that y to the p is congruent to x modulo multiples of p, and then you see that passing to absolute values, the absolute value of x is the pth power of the absolute value of y. So among all these generators, I can take pth roots, and therefore overall the value group is indeed p divisible. So this is some sense in which there's lots of p ramification occurring in my field. In fact, one can go further and check that if f is perfectoid, then it contains many compatible sequences of p power roots. A to the 1 over p, a to the 1 over p squared, and so on. So this follows from some standard type of p-adic approximation argument. If you take some element in OF, then modulo p, it admits as many p power roots as you like. So you extract lots of p power roots in this way, and then you p-adically approximate them, and some standard trick lets you form then lots of compatible sequences of p power roots inside the field itself. And using these types of compatible sequences of p power roots, we construct the tilt of the field. So I fix some perfectoid field. And I'm going to build from it some new valued field. Called the tilt of f. As follows. So as a set, I take all the compatible sequences of p power roots inside f. So let me write this as follows. I take the inverse limit over the p power map on f, or in other words, I just look at the set of all sequences a0, a1, a2, and so on inside f, which, as I say, are sequences of compatible p power roots. So I ask that ai to the p is equal to ai minus 1 for I bigger than or equal to 1. And by this remark that I made a moment ago, say there are enough such sequences in some sense. So I'm allowed to multiply two such sequences term-wise. That's fine. What's trickier is defining the addition law on this set, though. Let me write the formula down and then make some comments. So if I have two such sequences, a0, a1, and so on, I add them together to form some new sequence where the terms in this new sequence are given as follows. So the ith term in this sequence, I take the topological limit inside our complete valued field, so as n goes to infinity, of a I plus n plus b I plus n to the p to the n. So you have to check that this does indeed converge to some element in f. And here, if I weakened f to only being Henselian, well, there you'd already start to have some problems because now we're really using completeness in an essential way. So this is in fact, so let's say, a classical formula appearing in field theory that certainly goes back to the days of Fontaine and Wintenberger's theory of field of norms to define an addition law on these types of sequences. So one way to interpret it is that, so if my sequences, let's say, were in OF, then modulo P, this is just termwise addition. Modulo P, I'm just adding the terms of the sequence termwise, and then that's the unique way to lift termwise addition modulo P in a manner which is compatible with ensuring that we restrict ourselves to this set. So it's the unique way to do that, and that can be made precise by, let's say, an alternative algebraic approach to defining F tilde. Maybe it's safe to remove that, otherwise we're going to have the... we can just swap. So this one goes up, this one comes. And I've not really used the idea that the field is perfectoid. If I took any complete valued field, I could repeat this. There's any complete valued field of residue characteristic P, then this construction would still work and produce some new field. But if you took something like QP, the output would be very small, because there you don't have very many compatible sequences of P power roots. So I've defined the set, multiplication, I've defined for you maybe a strange looking addition law if you've not seen it before. Next we define the absolute value from F tilde. Again, it's going to be a rank 1 valuation where I take my sequence and I just look at the absolute value of the 0th term. Yes. Yes. And more generally, one observes that this map is in fact factoring through F, and this is what we call the untilting map, sharp, that takes me from F tilde back to F by sending some sequence to its 0th term. And this is multiplicative by definition of the multiplication, but not usually, well, let's be more precise. I can say, but additive if and only if I started with a characteristic P perfectoid field. If I'm in a characteristic 0 case, there's no way it can be additive. And then to summarize what one needs to check, well, one shows that, firstly, under all these laws, F tilde is a complete valued field with the same residue field and the same value group as what we started with. Moreover, it is perfectoid of characteristic P. So starting with one perfectoid field, probably in characteristic 0, we found some way to construct this new perfectoid field, now sitting in characteristic P, which we call its tilde. And as far as regard the proofs of this, well, the first assertion, namely that these laws, firstly that the algebraic rules really do make this into a field, that's just a straightforward straightforward manipulation of the definitions. To check that this is a valuation, well, it's clear that it's multiplicative. You've got to check the non-Archimedean inequality. So you've got to compute some absolute values of these types of limits of these sums of p powers. Okay, but I can pull the absolute value through the limit, and then you use the non-Archimedean inequality inside, and you conclude that indeed you again satisfy the non-Archimedean inequality. Then you've got to check that it's perfectoid of characteristic p. Well, you can easily see that it's perfect because by construction, any sequence admits a pth root. You just shift the sequence one to the left, and it produces for you a pth root of your original sequence. And again, I suppose you can directly input the addition law to check that 1 plus 1 plus 1 and so on, p times equals 0 inside this field. So here are a few examples. So if we started with perfectoid of characteristic p, so if f already had characteristic p, then tilting doesn't do anything. Maybe if one wants to be more precise, this untilting map is then an isomorphism of valued fields. Sorry?
Tilting is the equivalence of the category of something.
It's many things. So let's now return to the examples that I rubbed out. So let's tilt. Let me add all p power roots of p to qp. I complete the result. That was somehow the canonical choice of perfectoid field. And then I'm going to tilt that. And that will give me fp t1 over p infinity. Okay, I follow your notation and I complete it, in which the element t here corresponds to the sequence p 1 over p, p 1 over p squared, and so on. So that's a compatible sequence of p power roots. It defines an element of this field. And more precisely, I'm asserting that there exists a unique isomorphism of valued fields between this and this, which will send t to that sequence inside the tilt. So I had CP. That was my completed algebraic closure of QP. I can tilt that, and in that case, I'll get a completed algebraic closure of FPT. And this is, in fact, it's already not so hard, it's already not so easy, sorry, it's already not so easy to prove that the tilt of an algebraically closed perfectoid field is again algebraically closed. There's already some content in that statement. And let me just maybe cryptically write down related to fields of norms. Which is, let's say, the predecessor of the tilting correspondence due to Fontaine and Wintenberger. But I don't actually want to say anything about that today. Sorry? Roots of, I've got that one here. Do you want roots of unity? Oh, it's a bit trickier to write down what T is. Yeah. And you can, if you chase through the definitions, it's given to you, but it's given to you as some nasty limit along these types of expressions.
So in the second last line, and that is compatible with the other identification.
Yes. Yes.
By the way, if you do the tilt with the roots of unity,
yeah.
what is the isomorphism?
Oh, this is what I've just been asked. And so it's not so easy to write down what T goes to. I could chase through the definitions and write it down, but it wouldn't be very meaningful.
You identify with the same field on the right, but that means...
But in a different way, in a different way. Okay, no, I guess I can... Okay, maybe I can do the calculation at the risk of embarrassing myself. So let me take my curly zeta p infinity, and I'm pretty sure that this is again going to be fp t to the 1 over p infinity hat. And now I'm going to have to send so I can form the sequence as n goes to infinity of zeta p to the n plus I minus 1 to the p to the n for I bigger than or equal to 0. So there's the sequence. In fact, in some other formalism tells you that's what it's got to be. This one goes up. No, this one goes up. This one comes. Okay, so we started with our perfectoid field. We've tilted it to get another perfectoid field. If I started in characteristic P, I've not done anything. If I started in characteristic 0, I have done something. But there's still the question, even if I start in characteristic 0, in what way is F and F tilt similar? So I'm going to try to promote the point of view here that they're sufficiently similar that maybe one can detect this similarity using techniques of model theory. So firstly, as I already stated in the lemma, they have the same residue field and value group, and hence they have the same RV sort. But in fact, we can do a little bit more. They even have the same, let's say, thickened residue ring. So let me make this precise. Let me fix a compatible sequence of p power roots, say pi to the 1 over p, pi to the 1 over p squared, and so on in my field.
You mean the same RV just as a set?
Sorry, yeah, okay, I say sort, but I've already embarrassed myself. Same, why don't I just write same RV and then, except now you think it means a recreational vehicle and it doesn't make any sense. I'm not trying to make any, okay, what should I write to be correct? It's fine. Okay, good. So let me fix some sequence, some compatible sequence of p power roots where this first element could, for example, already be a pth root of p. So more precisely, I just want to ask that pi to the p, I want to ask the absolute value of pi to the p is bigger than or equal to the absolute value of p and strictly less than the absolute value of 1. I don't want it to be a unit, otherwise something stupid would happen. So then I can associate to this pi tilt, which is just the corresponding, well, it's exactly this sequence of p power roots, but viewed as an element of f tilt. Then the tilting map induces an isomorphism of rings between, so let me look at the ring of integers of f tilt, mod it out by this element pi tilt. And tilting will induce for me an action, as I say, although this untilting map is in general not a ring homomorphism, it will become one as long as we go modulo some element that eliminates all the problems appearing in the limits that appear when you define addition. And in particular, it will give me an isomorphism of rings between OF tilt mod pi tilt and OF mod pi. So this is the sense in which I want to say that these have the same thickened residue ring. So this is a non-discretely valued field, remember. So its maximal ideal cannot be defined by a single element. So here I have a lot more, let's say, I mean, it's some nilpotent thickening of the residue field. So not only are the residue fields isomorphic, but in fact you can have some canonically defined isomorphism between big nilpotent thickenings of the residue fields. And hence, at the risk of making another RV mistake, let me say that these fields even have the same thickened RV, by which I mean that I can look at the units inside the tilted field, and I can mod it out by the units which are principal with respect to pi tilt. And again, the untilting map will induce for me an isomorphism between the analogous object on the untilted side, which is it's a statement that contains more data than the identification of the standard RVs. Yes?
Is it okay if you just take pi to the power of p minus 1?
Pi to the power of p minus 1 here? It seems to me...
Does that correspond to joining just the fifth roots of unity?
I would need to think. I think no. Unless I've messed up a normalization somewhere. So here's another curious observation that I noticed while preparing the talk, which I really include just for the sake of the audience, is that F and F tilt, they have the same cross sections to their valuation as well. So more precisely, if I fix some p divisible subgroup, let's say H, inside the value group, so I could take the whole value group, but I can make a stronger statement if I allow any such subgroup. Then cross sections to the valuation from H to F are the same as cross sections to the valuation from H to the tilt. Which way is the easiest one to write down? Well, they're in bijection. For example, if I have, let's say, Tor is some cross section on the tilted side, then, sorry? Thank you. Then I can pull this back just by composing it with the untilting map. And one can check that this indeed defines a bijection between the cross sections on each side, which I found kind of curious. So in particular, if you have some language of valued fields, which includes cross section, then when you tilt, you still have a canonically defined cross section on the tilted side. So and finally, and perhaps most importantly, the two fields have the same arithmetic in some precise sense. So this is the theorem which in the classical form in terms of fields of norms is due to Fontaine and Wintenberger. And in the style of this presentation that I'm giving is due to Scholze, and states, so I continue to have my perfectoid field F, and states that if L is a finite extension of F, well, then FL is still a complete valued field. And the statement, which is already not so easy, is that this finite extension is automatically perfectoid. And when I tilt it, I get a finite extension of the tilt of F. Moreover, I get every finite extension of the tilt of F in this way, and this gives me a bijection between the extensions on each side. By sending my finite extension to its tilt, and hence, nope. And hence, by some Galois theory, I pick up an identification of the Galois group, the absolute Galois group of F, with the absolute Galois group of its tilt. So we believe that all arithmetic of a field should be contained in its absolute Galois group in some sense. So this is the way in which I wish to say that the two fields have the same arithmetic. So I promised I'd confine myself to a single board of speculation. Here it comes. And so deliberately trying to be imprecise, does there exist a language which somehow has to avoid addition on the field sort such that F and its tilt are equivalent, where I deliberately don't add any adjectives to language or equivalent so that you can interpret it however you like, mainly just to save myself. One clearly has to avoid addition on the field sort because we allow the case that F is characteristic 0 and F tilt is characteristic P. So somehow you've got to discard that phenomenon.
Unless equivalent is some kind of bi-interpretable.
Sorry?
I mean, there's a notion of equivalent which is bi-interpretable, which
okay.
doesn't mean that they have the same.
But then they are.
What?
But then they are in continuous logic.
Yeah.
Okay, so there may be already some precise answers to this question, more likely in the negative direction. I leave it on the board anyway. Ah, sorry, you're saying there's even some positive. Okay, well great. I didn't know that, so that one's ticked off. I didn't think this would be so easy. Okay, I guess maybe there's some tautological way to do it. But is what you're saying that there's even some non-tautological way to do it?
I think you were thinking about something like elementary equivalence, which is different. But since you left equivalent open...
Yes, I wanted to write elementary, but then I thought someone might immediately say, no, this is nonsense.
You can go towards bi-interpretable, and yeah, you need some kind of continuous logic, and then it's all right. I mean, for example, the level 2 bit vectors over a field in the field are the same from that point.
Okay, well then maybe the next question is also going to have a good answer. So I also thought the next question was some wild speculation, but if so, which is yes, if so, it's true. And I think you're going to tell me the answer to this is maybe true as well. Can we give a model theoretic interpretation to, well, let me see what I want to say. Let me take the set of perfectoid fields K such that, well, Okay, well, let me continue the theme of the first question and just write such that K is equivalent in whatever sense this means to F. But what I'd really be interested in is something a little bit smaller, so I can look instead at perfectoid fields K with the property that their tilt is even isomorphic to the tilt of F. So conceivably, in fact, as we saw in this example of adjoining p power roots of unity and adjoining, p power roots of unity and p power roots of p, I pick up, I lost the tilt here. I pick up the same tilt even though I started with non-isomorphic fields. And so in general, you can ask for some classification of all perfectoid fields which tilt to the same thing as the perfectoid field that I started with. And this is, the reason one cares about this is because this is identifies in some sense that I don't want to get into details about with the Farg-Fontaine curve of p-adic Hodge theory. So this is the central object these days in p-adic Hodge theory and attempts to geometrize the local p-adic Langlands correspondence. I can't write any more because I said I'd keep the speculation to one board, but it's very provocative to suggest that there might be some model theoretic interpretation of the Fontaine curve.
Point one no longer counts as a speculation, so you get to do one more.
Sorry?
Your point one.
Oh, it turned out not to be. You're right. You're right. No, I don't have anything else to say anyway. I don't have any further speculation to say anyway. I continue with something more precise. So I just wanted to spend a little bit of time, not much, on beyond the fields. And somehow the great power of this perfectoid and tilting machinery is that it's really not restricted to fields. You can actually do global geometry with the machinery in a sense that I'd like to explain now. Also so that I cover the theme of the conference, which is on Berkovich spaces. In fact, I'm going to be on adic spaces instead. So the building blocks, let me remind you, or tell you if you've not seen the theory of adic spaces previously, the building blocks for Huber's theory of adic spaces are pairs of rings R containing R plus such that, so R plus, pairs of, let me say pairs of topological rings such that my R plus is an open integrally closed subring of R, I guess I need technical hypothesis, such that each element of R plus is power bounded. Let's just do let me not say anything about the parenthetical hypothesis. I take an open integrally closed subring of R and I insist I want to restrict to the case of Tate rings. So I ask that there exists some element pi in this subring such that, well, I want it to be in the subring and I want it to be a unit in the ambient ring such that the topology on this subring is the p-adic topology, and maybe that actually gives me everything. I think combined with the other hypotheses, that's going to force the ambient ring to be R plus 1 over pi. So these are the sorts of pairs that I'm interested in. So these are the building blocks of Huber's theory of adic spaces. Indeed, if we have such a pair of rings, I associate to it its adic spectrum, spar RR plus, which is by definition the set of all continuous evaluations on the ambient ring R with value in any value group which are bounded in a strong sense on this R plus. That's the reason for the R plus. We'd like to just study all the continuous evaluations on R, but we need to cut it down slightly. And you cut it down by imposing that these valuations are bounded on this subring. And you mod it out by, well, the obvious notion of equivalence of valuations. And we topologize this by taking as basic opens those valuations with the property that the absolute value of f is less than or equal to the absolute value of g as I run over all f and g in my ring.
What is gamma?
It's not the same gamma. No, sorry, I thought about changing that. If that's going to lead to confusion, I better change it. So I should write more precisely pairs absolute value comma delta.
Continuous with respect to what topology?
The order topology on delta, yeah. And as I say, I allow this value group delta to be arbitrary. You can, but for defining the simplest sorts of opens, that's okay. Yeah. And then you refine it in various ways and check that other things are okay, but that's all right. And we call such a pair perfectoid if and only if, what do I need? We can choose pi. I came up with a clean definition. Only if we can choose this element pi to satisfy the following two properties. So firstly, I impose the same type of deeply ramified condition as before. I ask that every element of R plus mod pi R plus has a pth root. And then the analog, if I don't even give these things names, that's the analog of 2 in the definition of a field, and the analog of 3 in the definition of a perfectoid field. This was non-discreteness of the value group. I arrange this by insisting that p is divisible by pi to the p. So I wouldn't, for example, be allowed to take pi equals p. So quick remark that if I took some f as at the beginning, so it's a complete rank 1 valued field, then you can really check that I'm doing the same as before. F will be perfectoid in the previous sense if and only if the pair consisting of f and its ring of integers is perfectoid in this new sense. And we, just as for the case of fields, we can define the tilts of a perfectoid pair R and R plus. As before, I look at all sequences of compatible p power roots with the same multiplication and addition law. That defines for me then a new perfectoid pair R tilt containing R. Thank you. I need R to be, at some point R should be complete, if and only if, let me put it here, R is complete. And thank you. Yes, I could ask that R plus be p-adically complete. That's what it amounts to, yes. But they're topological rings, so I can just ask that they're complete in the general, where complete means complete in Hausdorff. And then as in the field case, we can pull back valuations. So if I have some valuation on R, I can construct a new valuation now on R tilt. And remember, the definition of this is the same as before. I'm just looking at all of my compatible sequences of p power roots, and I just pluck off the absolute value of the 0th term. And so this process defines for me a map from the adic spectrum of my first perfectoid pair to the adic spectrum of the tilt by exactly this construction. I take my valuation and I tilt it in this fashion. And I want to finish with this second theorem, also due to Scholze, which states that given a perfectoid pair, firstly, this is a homeomorphism. So the really hard part there is, I can never remember what the really hard part is, actually. It's all just hard, and somehow no one step is easier than any other step. No, but in fact, one of the hardest parts I've hidden away. So the adic spectrum has a certain canonical basis for its topology, which is more refined than this one here. And maybe the hardest part is actually the statement that not only is it a homeomorphism, but that under this homeomorphism, the two bases match up. And this is what's really hard, because this means you've got to start with certain elements defined in the tilt, and sufficiently approximate them here so that the valuations behave on the same way on the two elements. And it's a really subtle approximation. Sorry?
The same basis for topology?
Yes, yes. So this is a homeomorphism, but so avoiding the subtlety of these bases, let me just say that it induces, let's say, isomorphisms of sites. So I can look at either the analytic site on both sides, or I can look at the étal site on both sides. So in the case in which you take a field, this identification of étal sites reduces to theorem 1. But in general, it's a substantial generalization of it that really lets you do study global questions in p-adic geometry by tilting the characteristic p. Maybe I didn't state explicitly this new perfectoid pair is, of course, of characteristic p on the tilted side. So the idea is that then if you, let's say you want to study some smooth algebraic variety over QP, here's what you do. So locally around any point, you look like an étale algebra over some polynomial ring. Now you take p power roots of all of your polynomial variables, and you p-adically complete the result that you get at the end of this. This will be some perfectoid R in this sense, and you have some choice of an R plus. So this process of extracting all p power roots in sufficiently small neighborhoods lets you cover your smooth p-adic variety by perfectoid things. So informally, any smooth p-adic variety is locally perfectoid in some sense. And, I mean, you need some formalism to make that precise, but that's the crux. And then you can tilt all of these local perfectoids which you've used to cover your variety, and you study what's going on the tilted side using methods of characteristic p geometry, and then you untilt back. And the conclusion is theorems on your original characteristic side through characteristic p methods. I finished there. Sorry for running over. Thank you very much.